Hello everyone and welcome to this last video from the vectors topic. This one's going to be dealing with vector proofs. Generally these can be a little bit tricky and they are often discriminating questions, but the more of them you do, the easier it's going to become. And so in this video I'm going to essentially be going over some of the most common vector proofs that you deal with, so you can kind of see the method that we use, as well as kind of learning from those key proofs to adapt to other proofs. So these are like the kind of key proofs that you need to know, and they'll give you the techniques and skills that you need to prove other vector proofs. So the proofs that we're going to be going over in this one is proving that the diagonals of a parallelogram intersect at right angles if and only if it is a rhombus, that the midpoints of the sides of a quadrilateral join to form a parallelogram, and finally that the sum of the squares of the lengths of the diagonals of a parallelogram is equal to the sum of the squares of the lengths of the sides. That's a bit of a mouthful. It'll make more sense when I represent it mathematically, but those are essentially the three proofs that we're going to be going over. So without further ado, let's get straight into it. Okay, so this first proof is proving that the diagonals of a rhombus intersect at right angles if and only if it is a the diagonals of a parallelogram intersect at right angles if and only if it is a rhombus. Now what a rhombus is it's essentially a parallelogram where each of the sides are the same length. So if this is a parallelogram, a rhombus is a parallelogram with all equal sides. So a square would also actually be considered a rhombus as well. So all squares are rhombuses, but not all rhombuses are squares, is essentially what I'm dealing with there. So if I am writing out my proof, I always need to start with a required to prove statement. So the diagonals of a parallelogram intersect at right angles. We can write that as perpendicular. And then the if and only if implies an equivalent statement. So both the converse and the original statement are true in this case. So it is a rhombus. So what we're trying to prove is an equivalent statement here. The diagonals of a parallelogram are perpendicular if and only if it is a rhombus. So that's me essentially rewriting that statement in a mathematically accurate way with a couple of shorthands. So the easiest thing that we always do, usually in your test you'll be given a diagram already, and the best thing you do is you label it O, A, B, C. And now with parallelograms, generally what we like to do is we like to assign vector quantities to each of these. So for example, we might say OA, we're going to let OA, in this case, be equal to the vector A. Okay? And we're going to let OC be equal to the vector C. And this is what we like doing in vector proofs a lot of the time, because it kind of makes things easier to deal with if we're dealing with A's and C's rather than having to do the OA's, OC's, and everything of that nature. So I'm just going to draw up these diagonals like that. Another thing I should note is that a lot of the time in vector proofs you deal a lot with scalar products or dot products, okay? And so that is going to be a key proof here. In terms of scalar products, one of the key properties of scalar products that we are dealing with is the fact that if two vectors dotted together are equal to 0, that means those two vectors are perpendicular to one another. So that might be something that we deal with in this topic specifically. So now if we look at OB, OB is equal to OA plus AB. Now because we're dealing with a parallelogram, we know that AB and OC are parallel to each other and of the same length. So AB and OC are equivalent vectors. So we can rewrite this as OA plus OC, which is equivalent to A plus C. Now if we're dealing with AC, we're dealing with AO plus OC, which is the same as negative OA plus OC. Given that a vector in one direction, the negative of a vector is equal to the same magnitude of that vector, but in the opposite direction. So these AO and negative OA are equivalent. And so we can rewrite that again as negative of the A vector plus the C vector. And so if we want to prove that they're perpendicular, what we do is we do AOB dotted with AC. Okay, and that's going to be equal to A plus C dotted with C minus A. And if we expand that out, that's going to be A dotted with C minus A dotted with A plus C dotted with C and minus A dotted with C. Okay? So we can cancel these out because they're equal, and so we are ended up with C dotted with C minus A dotted with A. And based on my scalar product properties, I know that C dotted with C is equal to the magnitude of C squared, and A dotted with A is equal to the magnitude of A squared. And that's because, remember, that the dot product of A dotted with B is equal to the magnitude of A times the magnitude of B times cosine of the angle between them. If the angle between them is equal to 0, cosine of theta goes to 1. And so if you have A and A, so in this case A times 1, you of course have A squared, because the angle between the same vector is equal. And so here, C squared minus A squared equals 0 if and only if the magnitude of C is equal to the magnitude of A. And so this means that the only way that those that OB and AC are perpendicular is if the magnitude of this vector and the magnitude of this vector are the same. That is, this OABC is a rhombus. So therefore, essentially my diagonals of OABC are perpendicular if and only if the sides OA slash CB and OC slash AB are equal in length, i.e. a rhombus. And as a result, we have proved the statement that we were aiming to prove. QED. If you have any questions regarding this proof, make sure that you ask me in the comment sections and I'll go over it again and post some supplementary content. But otherwise, let's move on to the next proof that we deal with here. Alright, so this next proof requires you to prove that the midpoints of the sides of a quadrilateral join to form a parallelogram. So the first thing I want to do is I'm going to draw a quadrilateral. And I'm going to make sure that it doesn't look like a regular quadrilateral because we want to prove that it's true for every single quadrilateral. I have my required to prove statement. The midpoints of the sides of a quadrilateral join to form a parallelogram. And so now, just as before, I'm going to label each of the corners with a different letter, and I'm going to assign the midpoints here as this point here being M1, this point here being M2, M3, and M4. And now I can connect those up like this, and I need to prove that this M1, M2, M3, M4 is a parallelogram. So, as before, what I want to do is, if I'm looking at a parallelogram here specifically, what a parallelogram is defined as is a quadrilateral where the opposite sides are equal in length and in the same direction. Okay, so essentially what I need to prove is that M1, M2 is equal to M4, M3, and similarly that M1, M4 is equal to M2, M3, the vectors, that is. So if I consider M2, M3 is equal to M2, M3 is equal to M2B plus BM3. Okay, and that's all equivalent to 1/2 AB plus 1/2 BC. And so if I consider that, I can write that as 1/2 AB plus BC, and 1/2 and AB plus BC in this case is equal to AC.
So that's equal to 1/2 AC. Now I need to consider M1, M4. M1, M4, that will be equal to M10 plus O M4. And I can similarly consider that as 1/2 AO plus 1/2 OC. And AO plus OC, if I rewrite this as AO plus OC, AO plus OC is again equal to 1/2 AC. So therefore, M2, M3 and M1, M4 are the same vector. And because they're the same vector, that must mean, necessarily, that M1, M2 and M4, M3 are also the same vector. M1, M2, sorry. And M4, M3 are also the same vector. Okay, and that's necessarily because if we have these two vectors like this and they're the same length and the same direction, they're not exactly the same length here, but in this case here we can see that they are, if these are in the same length and the same direction, then these must also be in the same length and in the same direction. And as a result, therefore, M1, M2, M3, M4 is a parallelogram. And we've proved what we wanted to prove. Okay, and so this is the proof for the midpoints of the sides of a quadrilateral join to form a parallelogram. Now, if we move on to the last of these proofs, that is the sum of the squares of the lengths of the diagonals of a parallelogram is equal to the sum of the squares of the lengths of the sides. So if we consider this parallelogram here, this is a parallelogram. We have O, A, B, C. We're required to prove that the sum of the squares of the length of the diagonals, so that is OB in this case, and AC, so that OB squared plus AC all squared is equal to the sum of the squares of the lengths of the sides. So OA squared plus AB all squared plus BC all squared plus CO all squared. Okay, and so if we are looking at squares of the magnitude, generally what we're going to be dealing with is the dot product, because we know that the dot product of a vector with itself is generally is equal to the square of the magnitude of that vector. So now if we consider more specifically AC and OB, AC is equal to AO plus OC. And generally, again, as we did in the first proof, we generally want to refer to, we want to relabel these vectors, so we can let OA be equal to the vector A, and let OC be equal to the vector C. So this is a very common notation that we adopt when we're doing vector proofs. And so in this case, we know that AC is going to be equal to AO plus OC, which is equal to negative OA plus OC, which is equal to negative A plus C. Now if we look at OB, that is equal to OA plus AB, and because it's a parallelogram, AB is equal to OC, so we have A plus C. And so if we have AC dotted with AC, that's going to be equal to negative A plus C dotted with negative A plus C. And so that's going to be equal to A dotted with A, take A dotted with C, take A dotted with C, plus C dotted with C. And that is equal to the magnitude of A squared minus 2A dotted with C plus the magnitude of C squared. Now OB dotted with OB is equal to a plus c dotted with itself. And that is equal to a dotted with a plus 2a dotted with c plus c with c. And that is equal to the magnitude of a squared plus 2a dotted with c plus the magnitude of c squared, given the scalar product properties. And so if we have, and AC dotted with AC, of course, is equal to the magnitude of AC all squared, and OB dotted with OB is equal to the magnitude of OB all squared. And so if we add these two together, we have AC all squared with OB all squared. That's going to be equal to the 2 times the magnitude of A squared. And these two, the A dotted with C's, cancel out here. And we get nothing. And then we add 2 of C squared. Now, because we have a parallelogram, OA is equal to BC. So the magnitude OA is equal to CB, or the magnitude of OA is equal to the magnitude of CB. And so we can rewrite this 2A squared as essentially the sum OA squared plus the magnitude of BC all squared. And C is OC, but it's also equal to AB, and so the magnitude of OC is equal to the magnitude of AB all squared. And so we can rewrite this as we've done in our proof at the top. Our statement at the top, we can rewrite this as AB all squared plus CO squared. And here we've proved that the sum of the squares of the lengths of the diagonals of a parallelogram is equal to the sum of the squares of the lengths of the sides. And so here we've proved the statement that we wanted to prove. And we can put a QED. So these are the sort of key geometric proofs that you deal with using vectors. And they generally equip you with the skills that you need to answer questions related to different problems. They do get a bit of they do take a bit of getting used to, but generally notationally some of the key things I want you to look out for are that we assign vector values like A here and C to values like OA, the vector OA, to simplify things. And generally you will be provided with a diagram. In this case I've had to draw the diagram myself, and in some cases you may be required to draw the diagram as well. As you notice, there is a lot of use of the scalar product across all of these proofs, so that's something I would make sure that you revise, and always think about the properties of specific quadrilaterals when you're dealing with proofs. So for example, that parallelograms have two equal opposite sides, and the vectors have to go in the same direction to indicate that they're parallel to each other, for example. And there'll be other proofs as well that you deal with. For example, the scalar product being equal to 0, representing intersection at perpendicular angles, or right angles, sorry. But that's all for this video, and we'll move into the next video, next topic in the next video. So I'll see you then.